Hi everyone, this is Anushka and welcome back to my channel A in Economist. So if you are someone who is following my channel from quite a time, you will know in the previous few videos we have started off with specification error or what we call as specification bias, where we have already done the first two kinds of specification error in detail. Now, in the previous video, we have said that the specification error regarding 3 and 5, we cannot generalize them. We cannot find out general consequences of these two specification error, and hence we will not study this theoretically. So, in the previous video, we started off with the error of measurement as the fourth specification error, as the fourth and the final specification error. Particularly, we have seen what will be the impact of the specification error if the error is on y. Right. So variable y, if we do not know the actual value or the original values of the variable outcome variable y, what will be the impact of that? That we have discussed in the previous video. So today we will move ahead and we will see what will be the impact of the specification error in measurement in particularly variable x, right? So this was the agenda. We stopped at this place in the previous video. So we will start from here. We will see if x has error in measurement, that is, we need to introduce some proxy variable to explain our model, then what will be the impact of them. So let us start with the model as usual. So the model here looks like this. yi is the outcome variable. Then you have beta naught plus beta 1 x1 I star. Suppose this star is the original variable which is not directly observable basically, plus cy for all I. And we assume that all the assumptions as CLRM are holding. This is the true model. This is basically the true model or the correct model that we should follow in our context, in our purposes. But due to some mistake, since this x1 star is not observable, let me write it here. So it satisfies, this model satisfies all the assumptions of CLRM, but here this x1 star is not directly observable. Is not directly observable. So what we do instead, we have a measure of x1 star. A measure of x1 star. Measure means a proxy of x1 star. Say it is simply x1. Right? So instead of x1 star, which is the original explanatory variable, we will work with x1 star. And this will give rise to the what we call as the measurement error. So see, suppose the relationship is like this. E1, suppose E1 is the measurement error, it looks like x1 minus x1 star. Right? Say E1 is the measurement error, which looks like this x1 minus x1 star. Suppose I call this 1. Here, E1 represent the measurement error in x1 star. Right? So this is a similar thing that we have done in case of y as well. So in case of y, we take this variable to be y star, and then we have introduced another variable y. So here, this y variable is independent of any kind of measurement error. This y variable values are already available to us. But due to some reason, due to lack of information, this x1 star is not directly observable. That is why this error of measurement in the variable x is coming into the picture. So that is why what we do, we instead take a measure or a proxy of this x1 star, namely x1. That is how we have introduced this measuremental error, that is E1, which is simply x1 minus x1 star. Right? I hope this much is very clear to you. Now we will go into the different kind of assumptions that we need for this consequences, all the remaining consequences to derive. So let us see what could be the possible assumptions. The first assumption that we will talk about will be regarding this error of measurement, that is E1. So the first assumption that we will assume is expected value of this E1 will be exactly equals to 0, which basically means the actual values of EI can be positive, can be negative, it can be 0 as well. But we assume that on an average, the measurmental error is 0. Let me write on an average, the measurement error on an average, the measurement error in the population is exactly equals to 0, right? So this is the first assumption that we need to make. Now come to the second assumption. The second assumption will be the expected value of x1 u. U is the error in the original model. See, ui is the error term in the original model. So we'll assume that this u, that is the error term, that is completely uncorrelated with the variable x1. Also, u is completely uncorrelated with the x1 star. So whether you take the original explanatory variable or you take the proxy explanatory variable, it will be always exogenous in nature because it is uncorrelated with the error term in present in the model. Or you can alternatively write in this fashion: covariance of x1 u is equals to 0, or here you can write covariance of x1 star comma u is exactly equals to 0. Both are the same. It basically means that we shall assume u is uncorrelated with both x1 star and x1. Let me write it down. U is uncorrelated with x1 and x1 star, which basically implies that both x1 and x1 star, they both are exogenous variables. Basically, no endogeneity problem is there in the model, which is ensured by this particular assumption, right? So this will be the second assumption. Now let me go to the third assumption. The third assumption is known as conditional expectation assumption. Conditional expectation assumption. Here what we will say is that conditional expectation assumption means we will say x1 does not affect y, after x1 star has been controlled for. So notationally, if you see, notationally it will look something like this: expected value of y given x1 star and x will be simply equals to expected value of y given x1 star, right? So this is also a very unique assumption which is specific to this particular model, right? Which is specific to error of measurement in case of x, right? If you have error of measurement in explanatory variable x, so this also has to be a unique assumption that you have to make, which is known as conditional expectation assumption, which basically means x1 does not affect y. So see, if this x1 original variable is x1 star, so if x1 star is available to you, you do not need to look for x. That is what, in simple words, that is what it means. X1 is the proxy variable here, right? X1 is the, sorry, here it will be x1. So x1 is the proxy variable here, proxy variable or the dummy variable, and x1 star is the original variable that we must use. We should use in our purpose. But due to some reason, due to lack of availability of data, we cannot use x1 star. So, but this we are saying that here in this assumption, what we are saying is that if x1 star is known to us, then we should not look for x1 as the separate variable. So x1 does not have any impact on y if or after x1 star has been controlled. right? So this is what is known as the conditional expectation assumption. That is also a very crucial assumption. Now let me go to the next assumption, which is the fourth assumption. The fourth assumption says covariance of x1 and e will be 0, right? This is the fourth assumption, which says covariance of x1 e1 is 0, which basically means e1 is basically the measurmental error. E1 is also uncorrelated. E1 is uncorrelated with the observed measure. It is uncorrelated with the observed measure x1, right? So this is the fourth assumption. Now there is a consequential, assumption that comes directly from here. Covariance x1 e1 is 0. So if that is true, what you can say about covariance of x1 star and e1? Can you pause the video and think what will be this? So for that, you must need this relationship that we have defined earlier. E1 is simply x1 minus x1 star, right? So this is the relationship that we have defined earlier. E1 is x1 minus x1 star. Now we are saying covariance of E1 and x1 is 0. That is, E1 and x1 does not have any relationship. They do not have any relationship between them. So what can you say about the correlation between x1 star and E1? By this relationship, we know they has to have a relationship, right? So see, E1 is determined by the difference of x1 and x1 star. Now, if E1 and x1 does not have any relationship, that basically confirms that E1 must be having some correlationship between x1 with x1 star, right? So here, notationally, if you see, this will be simply not equals to 0. So both the covariances cannot be equals to 0, right? So that is what I am saying, that if since E1, x1 and x1 star has some sort of linear relationship among them, and we are saying x1 and e1 are not correlated, which basically confirms that x1 star and e1 is definitely correlated. That is why this covariance is simply not equals to 0, right? This is the fourth assumption. So all the assumptions are done. Now, what we do, we will define the new model. We will define the new model introducing the error of measurement. So the error of measurement, if you see, error of measurement was like this. E1 is equals to x1 minus x1 star. This was the relationship that we had. And what was the original model? The true model was this. True model was yi equals to beta naught plus beta 1 x1 I star plus ui for all I. So this was the original model. So how will you write the incorrect model? Incorrect model means the model with measurement error basically. So we'll simply substitute this xi star using this particular relationship. If you do that, you will get yi equals to beta naught remains as it is, beta 1 remains as it is. Now instead of x1 star, you will write x1i minus e1i. This is the new modification and ui remains the same. So you can simplify this further, that beta naught plus beta 1 x1 I, just I am multiplying the things, ui, and then minus you have beta 1 e1 I. Now you can combine this error terms together and you can give the name of vi. So if you do that, then the incorrect model becomes this: yi equals to beta naught plus beta 1 x1 I plus vi. This will be the incorrect model for all I. Where this vi is, let me write it here, where this vi is simply ui minus beta 1 e1 I. So this is again a composite error term that we have seen. So this similar figure we have seen in the previous video as well, right? So this vi is a composite error term. Now, if we know this fact, then we can find out if x1 is still in exogenous or not in this particular model. In this erroneous model, what will be the position of x? So covariance of x1i vi. So if it is 0, then we will say that yes, still X1 is endogenous in nature, exogenous in nature, otherwise we will say endogeneity problem arises. So let us see, verify that X1I, and instead of Vi, you will write this Ui minus beta 1 E1I. Now what you will do, you will take the covariance separately, X1I Ui minus covariance of X1I beta 1 E1I. Now covariance of X1I Ui, by assumption, this we have assumed to be 0. So this is 0. Then you have this minus beta 1 comes out, covariance of X1I Ei or E1I. Again, this thing we have assumed to be 0 in the assumptions. So altogether, what you can say is that this entire thing will come out to be 0. So there is no problem of endogeneity in this model in the presence of measurmental error, right? So this much is clear, that if X1I Vi is 0, which means there is no endogeneity problem present. X is still an exogenous variable in the model that we can use for our estimation purposes, right? And also, if this is 0, that also signifies that the OLS OLS estimation with X1 produces consistent estimates of beta 1, right? So this consistency property also remains valid if these are our assumptions. Now let us move ahead and see what else we can show. From our original model, we have derived this incorrect model. Beta 1 X1 plus U minus beta 1 E1. This was the incorrect model that we worked with, and this we assume to be Vi. Now what we can say, and we have also proved that covariance of Xi Vi is simply equals to 0. This we have proved just now. So what will be expectation of beta 1 E1? So what will be expectation of this? Now see why we are doing this. If you can prove that this expectation of this is 0, that is basically expectation of Vi. This is basically the expectation of Vi. If you can show that it is 0, you can directly say that the unbiasedness of beta 1 cap and beta naught will hold. Why this is so? Because see, so far all the models that we have proved unbiasedness for, we have seen if the expectation of the error term, stochastic error term is 0, then that directly helps in the derivation of the unbiasedness. So here we will not derive the unbiasedness, we will only prove that expectation of Vi is 0, which is the expectation of the stochastic error term in the incorrect model. If you can show that that is exactly equals to 0, then directly the result follows that the estimators, or the slope estimator and the intercept estimator, they will be unbiased in nature. So we'll do that. Take expectation individually, expectation of U1 minus beta 1, expectation of E1. So this is 0 minus beta 1, again this is 0. So altogether this is 0. So this basically gives you unbiasedness of beta 1 cap and beta naught cap holds, right? So this is done. Now we will only show the impact on the variance. So we have already shown that beta 1 cap is both unbiased and consistent. Now we need to show the variance. So variance of U minus beta 1 E1, you start with this, it will be variance of U plus beta 1 square variance of E1 minus beta 1 covariance of U E1. So it is basically sigma U squared plus beta 1 squared sigma E1 squared minus what will be this? This will be again 0. So this variance is simply sigma U squared plus beta 1 squared into sigma E1 squared. This is basically the error variance, which is not the least. So in the original model, true model, in the true model, the error variance was sigma U squared only. Sigma U squared, because U was the stochastic error term. But in this model, this is basically variance of V. We are finding out variance of V in the incorrect model. In the incorrect model, this is coming out to be sigma u square plus some square quantity, beta 1 square, sigma E1 square. But sigma E1 square is always positive because it is variance of the measurement error. This is variance which is positive. Beta 1 square is a square quantity. That is also greater equals to 0. So basically this error variance will be higher. Error variance. So let me write the error variance is higher due to measurement error. So this is another consequence, and the final thing that we will show is we know from the relationship is x1 is x1 star plus e1. Now what happens? If you assume the other way down, you say E1 and X1 star is equals to 0. Suppose I take the other way down. Suppose the third assumption that we have assumed that previously we have assumed that expectation of E1, X1 is 0. If that assumption is wrong and we assume that covariance of E1 and X1 star is 0, which is also known as the classical error invariance assumption. Then see what we will have. Then covariance of x1 and e1 will be not equals to 0. What will be the exact value? Let us try to find that out. Covariance of x1 e1 minus expectation of x1 into expectation of e1. Now expectation of e1 is 0 in all situations. So expectation of x1 e1. Now it will be expectation of x1, you can write at x1 star plus e1 times e1. So it will be simply x1 star e1 plus expectation of e1 square. So what you can say x1, now from this you can say that this expression is 0. This is synonymous. E1 covariance of e1 x1 star 0 means expectation of this expression is entirely 0. So you'll be left with only expectation of e1 square, which you can write it as this. So this will be the variance of the measurmental error only. Right? Now use the model again. Model is this beta naught plus beta 1 x1 plus u minus beta 1 e1. So covariance of x1 u minus beta 1 e1. How will this change? See covariance of x1 u minus beta 1 covariance of x1 e1. Now covariance of x1 and u is 0, and this we have just found out. So we replace that. So this will be simply minus beta 1. Now covariance of x1 e1 we just found out to be this. So it will be beta square. Right? So this is simply the covariance between x1 and b. Hence, if you assume that the classical error in variance assumption is holding, what you can see is that the OLS regression of y and x1 gives inconsistent result. So OLS regression of y on x1 gives inconsistent result. So these are all the properties regarding that. And the final thing, one final proof we will do, and then we'll stop today's class. One final result that I want to show you is that if you use the probability laws, what you can show, the probability limit of beta 1 cap in this particular model, you can show that this will come out to be beta 1 sigma x1 star square upon sigma x1 star square plus sigma E1 square. Thus, as n tends to infinity, beta 1 cap, what do you think? It goes towards what? As n tends to infinity, see, this entire term is a constant term, so it does not go towards beta 1. Can you see this? It tends towards all entire thing. It tends towards entire thing as n tends to infinity. That is why consistency is not there. Consistency is not there, but we can have this much that you can write from this result. What you can write, probability limit of beta 1 cap. You can write this in this way, beta 1, and then you have 1 upon 1 plus, you can take this here, sigma x1 star square. Now, depending on this ratio, you can get two different cases. Suppose the first case I write when sigma E1 square upon sigma x1 star square. Suppose this thing is strictly less than equals to 1, which is more realistic because this is in the numerator you have the variance of the measurement error, and in the denominator you have variance of the unobserved explanatory variable. So usually the variance of the unobserved explanatory variable should be more. This is a more realistic scenario. If this happens, then what can you say from this particular expression? We can say this basically implies beta 1 cap will never tend towards beta 1. So even if the sample size increases, let me write this, n tends to infinity, beta 1 cap will not converge to beta 1. This is case 1, and the final case is case 2, where you assume just the opposite. Suppose sigma E1 square upon sigma x1 star square, this is strictly greater than 1, or say sigma squared. So basically you can write, so this is less than equals to 1. So now if you assume, the second case would be sigma E1 square is strictly smaller. So basically this ratio is going towards 0. We are assuming sigma E1 square is small compared to sigma x1 star square, which basically means eventually this ratio is tending towards 0. In that case, if you see from this expression, if this tends towards 0, then this probability limit will tend towards beta 1. Then we will say beta 1 cap tends to beta 1 as n tends to infinity, then consistency holds. Then consistency holds because the probability limit of beta 1 cap goes towards beta 1. Right? So inconsistency. So in general, what we can say, what will be the conclusion? The conclusion you can say that the unbiasedness holds under error, measurmental error in X. Unbiasedness holds in all the situations. The consistency may or may not hold. So we have discussed both the cases. In one case. So depending on the assumptions, the kind of assumptions that you make, your consistency will vary. It may hold or it may not hold. And the third consequence will be the error variance will always rise. Right? So these are the three broad things that we can have, broad three consequences that we will have under measurmental error in X. Right? I hope this thing is absolutely clear. Now, if this consistency is not holding, then what could be the remedy? Remedy could be usage of instrumental variable that we will see in our future videos, right? Instrumental variable, simultaneous equation bias, all these are different topics that we will do in some other video, right? As of now, let me summarize everything that we have done. I know this might seem a little heavy for those of you who are very new to this, but let me summarize these things. And if you need this note, you can drop me a comment down below. I will give away this note to you if you want. Otherwise, you can take a screenshot from the screen. You can pause your video and take a screenshot, and that will also help you to understand. Go through the line, go to line by line derivation, whatever I have done, you will understand these things eventually, right? So we started off with the error, measurmental error in the variable x, where we have used the same approach. We said that the original explanatory variable is not known to us. That is why we have introduced a proxy variable, a different measure or as a proxy variable, which is simply x1. And they are related using this measurmental error E1. E1 is simply x1 minus x1 star. If you have this, in order to derive all the consequences, you need certain assumptions. Expected value of the measurement error is always zero. Then we have assumed for the true model, since the true model follows all the CLRM assumptions, it will be having exogenous explanatory variance. No endogeneity problem will arise. So U is uncorrelated both with X1 and with X1 star. So both the original explanatory variable and the proxy variable, U is uncorrelated with both of them. This is the second assumption. The third assumption we have done is conditional expectation assumption that I have discussed. The fourth assumption that we have done, so we have taken a look at both these assumptions. See, in the first case, we have seen if covariance of x1 e1 is 0, in that case what will be the consequences, and in the next part of the video we have discussed this. If covariance of x1 star e1 is equals to 0, what can be the consequences? So if you have noticed, we have used both these things. Let me show you. This is the incorrect model. We have derived the defined the composite error in this particular format, and we have shown that there is no problem of endogeneity in this particular model if the assumptions hold. Also, unbiasedness is holding, no problem in that. Only problem will be here that the error variance will increase. And I have shown you this distinction here. Now, if you take the second assumption, which is the classical error in variance assumption, where we say covariance of x1 star e1 is 0, if this assumption holds, then what will be the thing? Inconsistency will arise. So basically, we have shown in the first case, the methods are consistent, the estimates are consistent. In the second case, if you introduce this assumption of classical error in variance, then the model will have inconsistency. So consistency is not absolutely sure in case of measurement error. In some situations, depending on the assumption, it may hold or it may not hold. And I have shown you all the cases where it may hold or it may not hold. And then finally, we have gone into consistency in much more detail, where we have discussed the probability limit, in which situation the probability limit will go towards the actual population parameter, and in which situation it will not go towards the absolute parameter value. So in this way, you can do all the analysis regarding measurmental error in the explanatory variable x. Right? I hope you like this video. This video is adding value in your life. If you do, please like this video and do subscribe to this channel, A Economist. And I'll keep on bringing such useful videos for you. As of now, if you have any questions from this video, please let me know in the comment section. And in the next video, we'll go into the test of specification error, which is known as the Ramsey test. We'll go into that and we will see how to conduct that statistical test, right? So thank you so much for your time, and don't forget to like, share and subscribe to this channel, where I bring 2 to 3 videos, long form lecture videos every week for you. It takes immense effort and time to make such videos for you. So if you like this, then please show your support and love towards my channel and my endeavor, right? Thank you so much for your time, and let's meet you in the next video.